Welcome back. Now we're just going to continue right where we left off. So we had, you know, created a model and then fitted the model on the X train and Y train phi to create a binary classifier that classifies given an image whether the image is phi or not. So and then we did also predict on new different image, and we found that it was actually performing pretty good. Right now, how do we measure the actual performance? Now we cannot just iteratively keep going through all the different images and then see how many times it has got it correctly versus how many times it has got it wrong, right? So we cannot manually do that. However, there are a few different tips and techniques that people usually use in order to measure the accuracy of the model or the performance of the model. So let's quickly take a look at a few of them. All right. Let me just make some working space. Cool. Now let's quickly look at the cross-val score that we get from sklearn. So from sklearn dot model dot model oops, model selection import cross-val score. So what this does is it performs something called as um, cross k-fold validation. So let me just talk about that real quickly. Before that, let me just type the code out. So cross val score. Now we can pass in the model SGD classifier, and then we can pass in the X train and the Y train phi, and then we can give the number of cross val to be how much ever we want, and then we can giving the scoring metrics that would be accuracy. All right, so let me just let that run. Meanwhile, I'll talk what this is doing. So from a sklearn.model selection, import cross val score. So that model selection method has another method called the cross val score. So what that does basically is that it creates different cross validation. So k-fold cross validation, that is this cross validation means that we are splitting the training set into k different folds. So in this case 3, so we have given CV to be 3. So we are splitting the training set into 3 different folds, right? And then making a prediction and evaluating them on each fold that we create to see the metric. Now what essentially is happening here is, since we have 3 different folds, so that is 3 different k-fold cross validations, we have given the X train and the corresponding label, and we've also given the model that it is used to predict on. So this model has something called as a predict function. So internally this k-fold, this cross val score will take the model that we give, right, and then call the predict method on the given data, that is the train, and then confirms it with the corresponding label, right? So it does it 3 different times. So it takes different samples. They don't repeat. So this X train has 60,000 samples, right? So of those 60,000 samples, it takes 3 different samples. It takes samples every time. So since we have given 3 times, so it does this 3 times, and every time taking different samples, the corresponding X and Y, and then predicting it on the model. So we pass in that X, then predict, and then confirm that with the Y. So that is what this is doing, and then we want the accuracy metrics. We are querying for the accuracy metrics, and then we can see the output that it has about an average of around 96-ish percentage. So it is performing 96% of the times correctly. Now if we wanted, we could have 10 different cross validations, where we'll get 10 different accuracy metrics or accuracy scores that it does. And for these 10 different, so it creates 10 different folds, and then every time it creates it, predicts using the model, and then sees the corresponding value with the y-train phi. If the model prediction and the y-train phi prediction is correct, then we have the accuracy of 100%, right? So that is how the cross validation works. Now let's wait it out until it's until we get the output. Since it's 10 different cross validation, it takes time to predict and then give the accuracy. That is why this is not the most optimal way to do the performance measure, but nevertheless, it is still one way to you know do your performance measures. So you know now the second type is confusion matrix. Let that done while we talk about the next type of metric. So confusion matrix. Maybe I can create the cell into a markdown and then have right that will do. So in the confusion matrix, what we have is we have something called as true positives, true negatives, false positives, and false negatives. Let me just quickly write down the code for it. So there are few steps to be done in order to perform cross validation. So we can say from sklearn dot model selection import cross val predict, then we can say y train thread is equal to cross val predict of the classifier SGD classifier and the X train along with the Y train phi, and of course we pass in the cross fold or the cross validation. We'll keep it to 3. Now we got the output, right? Now you see why we don't usually keep too many values for this, because it takes quite some time to get the output. But all in all, we can see the average is around somewhere around 96, because we can see many 96%, right? So we can average it out to 96. But yes, so here also I am going to keep the CV to 3, so that we get the output quicker. Then we do from scalar dot metrics. We are going to import confusion matrix, and we can call the confusion matrix on y train thread. Oh, sorry, phi comma y train thread. So let me talk about cross val predict. Just like the cross val, the score that we did, right? The cross val predict function also performs k-fold cross validation, but instead of returning the evaluation scores, it returns the predictions made on each test fold, right? So it returns the prediction instead of the evaluation. Um, so this means that we can completely get a proper prediction for each instance in the training set. So we don't have to worry about just the accuracy, since it actually does the prediction and not just gives us the scoring. We don't have to worry about the evaluation scores, because it is making a prediction on each test folds, right? And then the output of that is passed to a confusion matrix, and then we get the output of the confusion matrix. So Now the confusion matrix, right? So if I copy it and paste it, now here for understanding purposes, we say true, negative, right? False positives, false negatives, and true positives. So what this means is, let me just, okay, this entire thing should be, okay, cool. So what this means is, let me just zoom in a bit so that it's visible. Okay. Here we have the confusion matrix. So in the confusion matrix, every row we can see is the actual value and every column is the predicted value. So here we can see the negative and positive. The same thing. We have negative and positive. Don't worry, make sure you understand this. All right. Uh, okay. Now, in every row, like I said, every row is the actual value and every column is the predicted value. So here we have negative, negative, right? So that becomes true, negative. And here we have negative, positive. So that becomes false positives because here the actual value is negative, but the model has predicted it to be positive, right? I hope that makes sense. Now, similarly, we have positive, negative. So that becomes false negatives because the actual value is supposed to be positive, but the model has predicted it to be negative. So here NP means the model prediction, here NP means the actual prediction. So if we correlate, that is why we get the matrix or the confusion matrix. And finally, we have positive as the actual value and the model is actually predicted correctly. So that is the true positives. So we can understand that there are true negatives of 53,892 and false positives of 687 and false negatives of 1,891 and then true negatives true positives of 3,530. So I hope this makes sense because this actually gives us the how well the model is performing. So we can see that it gets it incorrectly 687 times for false positives. So that is the prediction is actually negative, but it has predicted it to be positive, and 1,891 times as false negatives. That is the output is actually positives, but it has predicted as negatives. So in our case, we can think of it like the output is actually 5, right? But it is predicted as not 5, whereas this value represents the output is actually not 5, but the model has predicted it to be 5. So we get the true here and we've got the not true here. So I hope that makes sense. You know that is the confusion matrix and this is the cross validation. Let me just open up you know add a markdown and then put that here. So we have cross validation, we have confusion matrix, right? And then we have something called as precision and recall, right? So let's just code that as well. So I'm just going to change this into a markdown so that so precision recall. So we have this function as well. So from sk learn dot metrics import precision score and recall score. Uh, then I'll add a code. So we can just say precision score. We can pass in the again y train phi along with the y train red, right? Uh, then just maybe call the print function on it, and then also get the recall. So recall score is again y train phi comma y train red. So let me quickly talk about what precision and recall is. So for precision, we have the formula precision is equal to true positives divided by true positives plus false positives. Whereas for recall, the formula is true positives divided by true positives plus false negatives. So this gives us the precision, that means how precise the model is, and this gives us the recall. And you don't have to manually implement this. We have the sklearn.metrics that has already implemented that for us. So we just have to query it and then get the output of it. Right. So uh, that is pretty much it. Now we also have something called as the F1 score, which I'll quickly talk about. And change this to markdown. Right. So F1 score is as follows. So we can just import it from the sklearn itself. Sklearn dot metrics import f1 score, right? And we can call the f1 score by passing the same thing y train phi comma y train red. So how do we calculate f1 score and what is the f1 score all about? Let me change that to markdown so that it does not throw an error. So f1 score is calculated as follows. So we have 2 times, so we can say 2 into, we have precision times recall divided by precision plus recall times 2. So that is actually equal to true positives divided by true positives plus false negative by 2. So don't get confused. You know, uh, so this is how we calculate F1 score. F1 score basically has as favors classifiers that have similar precision and recall. Usually people get the F1 score to see how well the general overall performance of the model is. but precision and recall are also pretty good identifiers. You ideally wish to have higher precision. That means we have the model performing well and it is precise more number of times. All right. So that is about the performance measures. So we have cross validation, confusion matrix, precision and recall, and finally we had the F1 score, right? So we had the F1 score. Now in the next tutorial we are going to talk about different types of classification, that is multi-class, multi-label, and multi-output classification. We're not going to perform any projects or any example on it, but we'll just talk about the theory uh, by giving some examples so that you guys completely understand. All right, so till then, take care. Bye bye.